We have been looking at irreducible tensor operators, and to look at what we had done last time, we had talked about the fact that with just O3, or issue 2, the rotation group, if we look at the representations there on a space J sigma, which is written this way, then we can think of J and sigma as being created with an operator A dagger J sigma on the vacuum. This then becomes a raising operator that raises one from the vacuum to a one particle state with spin and its z component, J and sigma. There's a comparable operator A J sigma, and such that the A dagger and the A form a a harmonic oscillator type algebra of A daggers and A's where their commutator is equal to 1. We can then look at how J squared, Jz, and J plus and minus behave in their commutator with respect to this A dagger operator. And if we assume that these operators, in fact, acting on the vacuum give 0, this defines the commutation rules of the A dagger operator's Lie algebra with the J squared Lie algebra. So in fact, we can then refer to this other Lie algebra of the A daggers and the A's as irreducible tensor operators which have this well-defined behavior under J squared and Jz. We can generalize this to hold for other types of tensors. This result is much more pervasive, to continue with our work, is much more pervasive and richer than one might expect because it extends the Lie algebra to encompass other operator structures. In particular, one can now see that just as the A dagger and the A were an irreducible tensor operators under issue 2, or the rotation group, we can now see that more generally we can take the 4 position x mu or x lambda, which has well-defined commutators exactly like a vector representation under the homogeneous Lorentz group. And this x mu and likewise the p mu for the 4 momenta are 2 irreducible tensor operators that have well-defined commutation rules with our homogeneous Lorentz group. So another deep aspect of this is the fact then that the representation space of a Lie algebra can itself be a collection of operators that in itself defines another Lie algebra. Thus one Lie algebra can be the representation space of another Lie algebra. Perfect example of that is the entire XP1 algebra, the Heisenberg algebra, which can now be seen as a vector, and a scalar under the homogeneous Lorentz algebra. It's even more complex when one sees how this circles back upon itself. Likewise, using the Heisenberg algebra, XP and 1, we were able to construct the homogeneous Lorentz operators. And so out of each of these, we can define the operators for the other one. Let's kind of now summarize where we are and re-examine our work with both the Heisenberg Lie algebra and the Lorentz Lie algebra. We can say generally that quantum theory is founded fundamentally on the fundamentally important commutation rule xp is equal to I times capital I, where capital I commutes both with the x and p and has the spectrum from plus to minus infinity. It behaves like a Casimir operator, and we choose only that one irreducible representation where capital I has the eigenvalue h bar with that one eigenvalue. And we stay in that space, and none of the operators transform us out of that space. We can take that and then extend it to 3 and then furthermore to 4 dimensions to have an x mu, p mu, and capital I Lie algebra of 9 operators that forms our foundation of quantum theory. Special relativity is then founded on the premise that we have an x mu which is x naught, x1, x2, x3, where x naught is ct, and an energy momentum 4 vector, p mu, where p naught is equal to E over c, and that these 4 vectors under the set of transformations leave this invariant form unchanged under the transformations. That then defines the Lorentz-Lie algebra, which of course includes O3 as a subalgebra, leaving the vector part squared as invariant. The commutation rules of that are then defined from the behavior of the x's and the p's, and we can from that derive the Lorentz transformation which it generates, L mu nu, for the Lorentz transformation, the hyperbolic sines and cosines, as well as the sines and cosines for the rotations. This is explicitly given in the form where the L's are e to the psi times m, where m is the generator for the Lorentz, m is the Lorentz-Lie algebra, and L is the Lorentz group. Taking those as infinitesimal, we can then write those in the following form, which we've already done. So, all in all, our quantum theory is defined by the Heisenberg commutation rules for that Lie algebra, for the Heisenberg Lie algebra, and special relativity is defined by the Lorentz Lie algebra. And these integrate together in a very coherent system of relativistic quantum theory with a, I guess what we would call the X, P, I, and M Lie algebra, where we have the total angular momentum m here and the position and momentum 4 vectors here. So altogether now we're putting these concepts of the relativistic 4 position, 4 momenta I, and the Lorentz transformations for the total angular momentum, what we might call the XPI, that's 4 position, 4 momenta, and I, and the M, which the M mu nu forms the homogeneous Lorentz algebra, all together into one larger Lie algebra. And the L mu nu that we just spoke of transforms, provides the transformation for an infinitesimal change, which we define as e to the lambda times that Lie algebra, gives us our Lie group. And in general, this is the relationship between a Lie algebra. E to the lambda times the Lie algebra gives us our Lie group, and it gives us the connection between the two. Since this is the Lie algebra, it means that we take any one of these elements or any linear combination of these elements, because you will recall that a Lie algebra is in fact a linear vector space. So we have 4 of these, 1 of these, and 6 of these. So that's altogether, that's 6 plus 4 is 10, 14, 15. So this is a 15 parameter Lie algebra that contains the relativistic concepts in the homogeneous Lorentz group and all of quantum theory with x and p in a 4-dimensional notation. And so in general we could take any linear combination of those 15 elements, 15 elements, and so we would have 15 different parameters here that give us any possible member of this Lie group. And that gives us the connection. By taking those, we uncover the Lorentz generators, matrices in the Lie algebra, from which we can derive the commutators of the m's and the m's, and therefore the Lorentz Lie algebra. Now, as we previously have shown, we can define the Lorentz Lie algebra m mu nu to be the total angular momentum 4 tensor. And we then define L mu nu to be x mu p nu minus x nu p mu as the orbital angular momentum 4 tensor. We then define S mu nu as m mu nu minus L mu nu. Thus it is the total angular momentum minus the orbital part, and we call that the intrinsic spin angular momentum or intrinsic spin tensor. it's easy to show that the commutations of the m's among themselves is identical to that the l's have among themselves, and which is identical to what the s's have among themselves. And so the form of the m commutators, the l's, and the s's is exactly the same in terms of the indices. And that gives us the total representations of this a total set of commutators for the S Lie algebra, which is now separated from, since the s's commute with the x's and the p's, separates that from the x's and the p's. Thus the 4 position x mu and the 4 momenta p mu and all of the 3 rotations plus the 3 Lorentz transformations are all embodied in this one Lie algebra now. By separating that algebra into the 4-dimensional Heisenberg algebra and the homogeneous Lorentz Lie algebra, we can find all of the representations of this Lie algebra. This algebra right here. That's what we want. How do we do that? Well, because the s's commute with the x's and the p's and the i's, we then end up with a product representation where we have the xp I Lie algebra representations here, and we can choose either position diagonal or 4 momentum diagonal as a cross product with the s's, the s mu nu, which is the homogeneous Lorentz algebra of the b0 b1 s sigma. And so we can take the outer product of position with spin or momentum with spin either way. And either of these gives us a basis in the space for the representations of the XPIM Lie algebra. The internal quantum numbers for the mass, which is k mu is m squared c squared, and the spin arise automatically from the Lie algebra structure. But the fact that we get a continuum of these masses and discrete spins is allowable implies that there are other constraints or restrictions that are needed in order to derive the real world. Now let me discuss what I mean by that. As we look at all of these representations, here for the homogeneous Lorentz group, over here for the quantum mechanics associated with that spin for space and for space and time here, and for energy and momenta here, we find this whole algebra has a richness that certainly accommodates everything in the physical world. In particular, the mass has a continuous spectrum from plus infinity to minus infinity. We have never found a particle with negative mass, but that is potentially allowed here. We do find particles with negative energy as antimatter, but the mass here, even considering the positive mass, the masses have a continuous spectrum, and the masses are not connected with the spins. Well, this presents kind of a problem, because we know that for example, that we have spin 1/2 particles that have specific masses, such as the electron and the proton, which are highly stable. But that restriction does not come out of this theory. In fact, we are allowed to have any mass for any possible spin representation. Furthermore, we have all of these very, very complicated spin representations, both unique spin and mixed spin, all of these occurring for any mass, and this is too rich. There therefore must be other changes. These could be in the form of constraints on the Lie algebra, or an alteration of the commutation rules of this Lie algebra that somehow or another restrict the system so that only for certain masses and only for certain spins do we get the physical world. No one knows how to do this yet. But that's kind of a challenging problem. It's at least good that we have a system that's rich enough to embody all of the current phenomena as we see it. I think central to this also is the fact that these algebras have H bar and C, our quantum theory and our relativity, guaranteed as invariants according to the Lie algebra commutation rules. And therefore we might anticipate that when there is a third fundamental constant that's identified, whether that's the gravitational constant or whatever, that constant will probably emerge in an integral way with the commutation rules for this extended Lie algebra. So, can I summarize this? In summary, we might say we want to look for alterations of this foundational Lie algebra at some point when it's appropriate that restrict the mass spectra, that restrict the spin spectra, so that we get something closer to the real world. There's also one more degree of freedom, since we have mass, length, and time that all have total freedom here. By selecting h bar and c as fundamental constants, we fix the scale of two of those, but not the third. The fixing of the scale of the third one of those variables will probably result in a new fundamental theory in physics, and it will probably be embodied in commutation rules that are extensions of these and an alteration of these. Let me address just for a moment the relativistic Heisenberg Lie algebra in 4 dimensions. That generalization is basically easy because we're going to take space and time, x mu and x nu, to all commute, as well as p mu and p nu to all commute, with p mu and x nu is equal to I times capital I times g mu nu, where g mu nu is the metric tensor. Capital I will then be we'll then select that one irreducible representation where capital I has the value h bar. That will mean, in essence, that the 4 dimensions are totally independent and decoupled, except for having a common value of I as an eigenvalue. Therefore, we can look at assuming that h bar is written in here and understood in every one of the one of the ket and bra vectors that we have in our representation space. We can have a position eigenvector or simultaneous 4 momentum eigenvector. The scalar products take the form of the 4-dimensional Dirac delta function, and the 4 momenta likewise take the form of the 4-dimensional Dirac delta function. The completeness relationship takes the form that the integral over all space and time of y mu is equal to 1, and d4k of all the 4 momenta is equal to 1. Thus we can write an expansion of a state psi in the following form, expressed over all 4 momenta, or likewise over all 4 position. The scalar product then takes the form in momentum space of integral of d4k between a vector psi and a vector phi star. That gives us our concept of scalar product and completeness relation, but there are some subtleties here that need to be addressed. In this theory, the dynamics is carried forward by proper time. And the proper time for a particle works well for a single particle, but does not work well for a dynamical theory. It is not known how to take a proper time theory where you have a clock that sits on each particle and build a relativistic quantum theory in terms of that. Whereas the group theory works very well and all the dynamics works very well as long as you have one particle, or even one particle, say in an electromagnetic or other type of field. To have 2 particles when you have 2 values of proper time is an unsolved problem. However, this foundation gives us a kinematical type of foundation for dealing with the Lie algebras and other aspects of the problem, so that one can lay this out and perform a separation that we'll see is a very useful way to approach physics by using position, momenta, and then the Lorentz transformation separated from that is a much easier way to look at the foundational states than to try to approach it from the point of view of representations of the Poincare group. Now, the Poincare group are included in this group, and we'll see in a minute, consist of the algebra between the p's and the m's only, where that becomes a symmetry group for the system. The richness of this XPIM Lie algebra is really vast because it includes, as I mentioned before, the entire Lorentz Lie algebra and the four-dimensional covariant Heisenberg Lie algebra. If we omit the X mu, as I just mentioned, we will then get the Poincare Lie algebra, which is the symmetry group for systems consisting of all rotations, Lorentz transformations, and translations. Although the Poincare Lie algebra, which is the Heisenberg Lie algebra plus translations, is the symmetry Lie algebra of relativistic quantum theory, because this X is omitted, you can't really form this angular momentum 4 tensor. And since we can't form the angular momentum 4 tensor, we cannot subtract it from the m mu nu and form the spin tensor, which separates and commutes with both x and p. Thus, the treatment of spin is very difficult in the Poincare Lie algebra. We have to, in fact, as we will see later, utilize something called the helicity operator. And it's just more difficult to deal with it, and we can't see as clearly all of the different representations inherent in the homogeneous Lorentz group. So we argue that it's really inappropriate to omit both the space and time operators, x mu, from the fundamental Lie algebra of observables. We know that we have to have observations of position. We have to have, an algebra of operators associated with position and of time in order to be both consistent with quantum theory and consistent with an invariance between space and time required from the Lorentz transformations. Space and time obviously are going to mix up with one another when we go from one frame to another, and we know that space operators, x, y, and z, with certain commutators with p, forms the foundation of quantum theory itself. So it's essential that we bring in these x's, even though we know that the dynamical theory associated with a system based on this in terms of dynamics is not yet solved. We can use this algebra as the foundation of our kinematics. In fact, it is critically important that our position operators be there, because, as I've mentioned before, all of our senses are based upon things that occur in space and time. So we need to see the wave function expressed in space and time in order to have any kind of intuition as to what these functions mean. When we say that we have a wave function, psi of x, y, z, and t, we need to be able to represent that wave function in terms of those variables and not just in terms of other variables which are not as intuitive. We can't intuitively think of in a visual type of sense the wave function in momentum space. We know it's composed of relatively different amplitudes of different momenta, but in terms of a distribution in space, it is essential from our intuition that we be able to take all of these functions and project them back onto a space and time dependent framework where those variables are diagonal in order to have a physical intuition of what these are like.